Okay, we should be good. Sorry about the slide presentation. I don't know why, again, why it's somebody's choosing to remove it. Okay, Araja, the stage is yours. I'm here to support in all
Hello,
ways.
everybody.
Okay, Araja, I'm not hearing you.
Can I start now?
Yep, I can hear you now.
Okay. So I will be presenting my views on ingestion and native vector generation. So first, let's then I will continue my views.
Go ahead.
Step into phase one of blueprint, ingestion and vectorization. And in traditional application development, if you wanted to generate a vector embedding, your application layer had to fetch the text from the database. And to make an HTTP call, external AI service like OpenAI, we handle API keys and we wait for the response. Then we push that vector back into the database. This introduces network latency, uh, creates massive security liabilities, and because of these API keys, uh, API keys floats around the application code. So, SQL AI capabilities will completely eliminate this risk using a feature called create external model. What the create external model does is allows us to register an AI endpoint, such as an Azure OpenAI, which embeds deployment, and what it does is it directly inside a database schema. And by doing this, we centralize and log our API credentials into the secure database engine. So database administration can manage access, can rotate keys, and it can also monitor endpoints. While developers get a clean, abstracted way for the model without ever seeing raw API key. Now, we'll be talking about native vector generation, AI generate embeddings. So once that external model is configured, that I have discussed previously, now we actually transform our unstructured data like product descriptions or customer reviews into vectors. And we use a powerful function called AI generate embeddings. Now, what this AI generated embeddings does is functions as a game changer and it operates directly within your standard select and or wait queries.
Araja, I just want to make sure we're tracking with the slides since I'm moving the slides for you. I've got us on the paradigm shift. Is that where we should be?
I'm not able to present the slides and also I'm not able to see the presentation that you are sharing.
Okay, so can you see the present? Can everybody see the presentation? Okay, yes. All right, so Aradia, I'm on the I'm on the paradigm shift slide where we've got legacy paradigm versus modern paradigm. I'm getting lots of people can see the slide presentation. Um, so we're at 2 of 15, but I can definitely move it to track what you're saying because what you were saying wasn't kind of matching what was on screen. So I just want to make sure that I'm moving ahead and following you. So then we've got the data lifecycle blueprint, phase one, phase two, phase three, phase four. Do you want to just, can you see that? Do you want to bring us back there?
I'm only able to see the black screen, like it's I'm sharing the screen that is visible to me on your personal window.
Yeah, I'm on slide 3 of 15. I just want to make sure we're tracking.
Okay. Yes, now it's visible.
Okay, just tell me when to move it.
Okay.
If if you can pick up here, that'd be great. So what I see in front of me is the
So
data life cycle blueprint. Yep.
okay, so this data lifecycle blueprint has phases: ingestion and vectorization, storage and mathematics, organization and retrieval. Now we will understand this strategic shift toward native AI databases. And when building an enterprise grade AI or retrieval augment generation, that is RAG system, the data cannot simplify the data cannot simply dump into a table. So it must follow the structure. It should be highly optimized pipeline. So this pipeline consists of four different phases that I previously discussed, that are vectorization, mathematics, and each phase relies on specific SQL capabilities that maintain speed, precision, and security. By standardized workflow, we ensure that whether we are handling a few thousand product description or hundreds of millions of customer interactions, our database that we our database remains lightning and it structurally sounds fast. So we will be discussing ingestion and vectorization in detail. So the blueprint begins from the phase one, that is ingestion and vectorization. And when raw unstructured text such as internal documentation, support tickets, or product reviews enter our system, it is immediately routed through our registered external models using TSQ. What it does is this ensures that every piece of incoming data is instantly paired with its mathematical meaning at the point of entry. So it brings us immediately to phase two storage. And once the model generates a mathematical array, it must be stored efficiently. And in the past, uh, what the developers did in past was they restored the storing vectors as massive strings, text or custom JSON nodes, which uh, which slowed their query performance and uh, floated the database size. So to we utilize a native vector DB under the hood, the SQL engine stores, and what it does, keys arrays in a highly optimized binary format. This optimizes memory consumption and allows the CPU to execute mathematical calculations directly on the data without needing fixed strings.
Let me know when you want me to
Now
advance the
we will
slide.
move. So, I'm on previous slide only. I will be talking about organization and retrieval, that is phase three.
Is that good? Let me know when you need me to
Yes,
move
yes.
it.
Okay. Once our vectors are securely stored, we encounter a massive engineering challenge scheme. And it's a millions of rows of data. Calculating similarity across every single row for every single user query is mathematically exhausting. So, to resolve this, we bring organization that is phase three, which resolves this problem. Now let's talk about the phase four, that is retrieval. And this is where the magic happens because the user here inputs a natural language question. The system dynamically converts question into query vector, which passes it to our disk and index and uses highly optimized semantic search syntax to pull the most contextually relevant records instead. Four-step lifecycle seems complete, operational, final for any modern database AI system. So this is all about data lifecycle blueprint. Now I request to please move the slide. So now we will be talking about establishing the secure AI bridge. See the command, mechanism, and security inheritance. So the mechanism here is register an external AI model endpoint directly within the database. So now let's see the how to establish the secure AI group. So that interference with AI or retrieval augment solution that is RAG system. Data cannot simply be dumped into a table. It must follow structured, highly optimized pipeline. And this pipeline consists of four distinct phases: ingestion, storage, organization, and retrieval that we have discussed previously. And uh, instead of leaving our vector unorganized, we build sophisticated navigational structure. We call this as DISCAN, that is distance-based approximate nearest neighbor algorithm. It organizes the vector space into a highly transversable structure, which is fast SSD storage, and it ensures that when a search query occurs, the system doesn't scan the entire database. So it makes the system fast, and instead of swiftly moves across the index graph, it finds the closest match, and that too within few milliseconds. So now native vector generation. With seamless integration. So, native function that calls the registered external model to generate vector embedding directly within its code. So, with native vector capabilities, we completely eliminate this developer friction using a single segment PSQL function that you can see the command AI generate embeddings. Now, what this function does is acts like a native translator within the SQL query engine. So, what it does, it bridges the gap between the unstructured human language and the highly dimensional vector map. And this beauty of this design is that it starts away all the underlying complexity. And as a developer, you don't need to learn a new programming language or manage complex external integration pipelines. If you know how to write a standard SQL, you already know that how to generate this AI embeddings. So now see how AI generate embeddings works. So let's look at how this function operates in the hood when you execute query containing AI generate embeddings. You basically pass two primary parameters, the name of the external model registered and the raw text data font. So SQL engine takes over from there and it dynamically packages your database text, just manages secure HTTP handshakes across over 45 grids to the AI endpoint. It transmits the payload. When the AI model sends back the high dimensional numerical array, the engine automatically intercepts the response and extracts the raw array and delivers it straight to your query context. Okay, so the mathematical output we get is the uh, returns an ordered array of floating point numbers, and if you're using an enterprise grade model like OpenAI, for instance, adding three small that array is exactly 1536 dimensions long. So every single one of those 1536 numbers represent a specific coordinate in a massive abstract semantic space. So let's move to the next topic, that is the mathematics of similarity, vector distance metric, vector 1 and 2. Okay. So once we have our vectors stored securely in our native binary format, we enter the world of pure geometry. How does a database actually know that? How do I reset my password? And I am logged out of my account, meaning almost the same thing. So it calculates mathematical distance between the nodes. And in a high dimensional vector space, look for a look for geometric proximity. And if the concepts are closely related, your vector's arrow will point in almost the same direction or end near the same spot. To measure this closeness, the database engine provides three primary similarity metrics, each optimized for different data types and use cases. These same similarity, Euclidean distance, या फिर dot product. So the three core metrics, uh, let's break down these three metrics because choosing the right one is critical for your architecture and your DP-800 exam. So first, we have quotient similarity. So quotient similarity ignores the length of the vector arrows and focuses entirely on the angle. This is the gold standard for text and natural language processing. Why this is a gold standard for text? This is because the length of a extractor often correlates with document length. And if you have a short product description and a long blog post that are both about cloud computing, your vectors might have different lengths. but they will point in the exact same direction. So, since similarity ensures we match perfectly. Euclidean distance. So, this measures the literal straight line distance between the two tips vector arrows, and like pulling a tape measures from point A to point B. Metric is highly sensitive to magnitude and is heavily favored in computer vision, and it recognizes image pipelines and continuous numerical data. So the rule of vector normalization, uh, now please move to slide 8. So it's vector normalized is mathematically scales the length of every single vector down to exactly one. So we will be talking about standardizing magnitude now. Since we use our vector norm, vector normalized, and the problem that can be resolved using vectors is uh, vector with different magnitudes to distance calculation, and we can resolve this by using vector norm, which calculates the exact magnitude, and vector normalized scales the vectors so its length is exactly one, and we get the result that all the vectors land on the same unit square, optimizing the accuracy and performance of Poisson similarity searches. So when an embedded model outputs a vector, each number represents coordinate, but o- overall length, या फिर overall magnitude of that vector can vary drastically. The length of a vector is highly influenced by factors like text length, big your text is, and how is frequency of your word or pixel density in an image. So if we keep these magnitude unstandardized, we run into major computational problem that you can see in the image. Like imagine trying to find the closest star in the night sky. Some stars are moving closer and further away while others stay still. So the changing distance distorts your measurements. In a database, calculating similarity across vectors with widely different magnitude forces the CPU to perform heavy floating point arithmetic on every single query just for those differences. This drags from systems and introduces mathematical noise into our search results. So now we will be understanding vector norm and vector normalize. So to solve this, we must we must standardize our vector space, which we accomplish using two primary pre-SQL functions. These are vector norm, vector normalize that you can see in the slide. Difference between them is vector norm calculates the exact magnitude or the literal length of a vector using a Pythagorean theorem across all dimensions, and it gives us a single number representing vector's total length. So this vector normalize, what does is it goes a step forward and it takes the magnitude and uses it to vector down so that its mathematical length becomes exactly while preserving exact direction in space. So let's look more into vector normalize. So think of it like taking a collection of arrows of all different lengths and cutting or stretching them so they are all exactly 1 meter long without changing where they are pointing. So by applying this vector normalized over vector columns during the ingestion phase, we eliminate the magnitude as a variable entirely, and every single piece of data in our database is now a level playing field. So the solution for this is the unit sphere. What happens to our data geometrically when every vector has a length of exactly 1 is it falls perfectly on the surface of a multi-dimensional unit sphere. So this creates an incredible architectural advantage when all data points are logged onto a unit sphere and the complex formulas for Poisson similarity and dot product simplify and become completely identical. This means that we no longer have to choose between the high accuracy of possibility and the raw data speed of the problem. And so by standardizing our magnitude, we get the database can execute lightning fast dot product calculations the hardware level while delivering perfectly accurate semantic search results to our users. So now let's move to phase three, that is exact versus proximate search. Please can you move the slide to exact versus proximate search?